puse un archivo PDF en Teams, donde hay archivos, files. Entonces, yo vi allá el programa del curso. No tengo acceso, puede ser que Jill pone las clases en bloque neón, pero no tengo acceso. Si ustedes entran allá en la carpeta de files, pueden descargar la presentación de hoy. Bueno, voy a compartir mi pantalla. Ahora, ok. Y voy a cambiar el idioma. So, thank you for being here with me. And what we'll look at today, we'll look at the use of remote sensing in mineral exploration. That's the idea. And as I was telling you, I will not focus. I mean, of course, we will have a focus on the remote sensing technologies that are used. But I want to put this into a larger context. So what I'm going to do, I'm going to show you what the current exploration technologies and methods are, and what the trends in exploration methods are. And then I'll show, these are things that you know a bit about remote sensing. And then we'll look at the actual use of these technologies in mineral exploration. And as you can see, we have here three topics to discuss: alteration mapping, structural and geological mapping, and this includes something called linament analysis. But more when we get there. Okay, so sit back and relax, because I just want this to be a good experience for you, so you don't have to stress yourself. I'll explain everything you see here. So what happens in mineral exploration today, we have different tools. None of them is perfect. That's the idea. It's very difficult to find the mineral deposits, especially if they are buried and we cannot see them, so they are blind. So most of the tools that companies use are here. You are going to see here a group that is more geological. It says prospecting, geological mapping, and stream sediment, soil, and rock geochemistry. So basically, companies will have people on the ground to map the ground, to take samples, and to prospect, to see if they can find any evidence of mineralization. Evidence of mineralization is not necessarily direct. It can be indirect in terms of alteration. But this is not enough. So companies have to rely a lot on geophysics. Now, geochemistry is a method, we'll see next term in the course, is a method that we can use with certain results. But again, it has its own limitations. So to reach certain depths, we need to use geophysics. And geophysics, you see this group as airborne geophysics. It is cheaper than ground geophysics. What's used today a lot are the EM systems, electromagnetic. So companies will employ all these methods, geochemical, geological, and geophysical, before they drill. Drilling is very expensive, and it happens only in one point. And what happens is, if you miss the target, then you wasted the money. So for this, companies have to build a case, to acquire data, to build a case, and to see where you have the highest probability of encountering mineralization. All right, so these are the core methods. Now, these methods are aided nowadays by technologies such as the GPS, the positioning systems. So you are looking into this in this course. So you can imagine, if you fly, you want to know when you sample the magnetic field, for instance, you want to know where exactly you were. So GPS helps a lot. Yeah, imagine how difficult it was before having this system. And also, when we get all this information into our computers, we use GIS software. So we can bring all this into the same project. and look at it. And now, and more recently, we have 3D imaging software. So people can use the information they acquired to try to build 3D images of the volume that is of interest. The volume can be directly the volume with a certain geochemical anomaly or with a geophysical source, yeah, as it is interpreted from the geophysical data, for instance. So this is what we are doing. Now, coming back to the topic of this course, the remote sensing methods. When we talk about remote sensing, we think about imagery from satellite or airborne aerophotograms. However, in a sense, the airborne geophysics is also remote sensing. Yeah? It's just different what field we basically sense. So some companies, what they do when they get to a new area to start prospecting and look for mineral deposits, they start from a regional scale. So they use satellite images. If airborne photography is available, they use that. Nowadays, unmanned aerial vehicles, that means drones, they start being used. So there are companies already offering services that like aerial photography. And now, right now, what's very hot is putting the geophysical sensors on the drones. So of course you get better resolution because the drones can fly lower and it's way cheaper. Now, there is something called linament analysis, which basically uses different sources of information, like anything from remote sensing, and also geophysical data, like magnetic data is very good for this. And I'll show you what is used for. So we will focus on these things, but you cannot really find the deposits directly with this technology. So it is kind of an additional technology companies use just to narrow down the search space, yeah. But then they have to focus using the other methods. So we start with remote sensing and then we go with the other methods. That's the idea. Okay, now just to show you something interesting in terms of the history of the methods that have been in use over the past century and more than 100 years, you see 120 years. So what happens, as you can see in blue, it's the basically the percentage of mineral discoveries. Yeah, that's what we look at these bars, and you see a percentage of mineral discoveries in each time interval. You see of 4 years or 5 years, sorry, 5 years time intervals. And what method led to the discovery? Led basically to the drill hole that was the discovery drill hole. As you can see at the beginning of the 20th century, we had the prospectors walking the ground and finding evidence of mineralization. Usually they call it gosan. So you get the rusty outcrops. So basically, it's the sulfide minerals that get weathered, and you get iron hydroxides, and that's what it is. So the prospectors did a good job in trying to find the deposits that were at the surface, exposed. So it was easier to find them. But as you can see, as we move up in time, we kind of run out of what's at the surface. So we have to use other methods to find this, to find the deposits. And you can see a combination of different methods here. But what I want to point out is what you see here at the bottom in red and in green. And in red and in green means geochemistry and geophysics. So people started using more and more geochemistry and geophysics because we ran out of choices. We cannot find the blind deposits that are buried. We have to use these methods to be able to spot the drill hole that would encounter the mineralization. Now, what you see in this very pale pink in the middle it says known mineralization. What this means, you know that there is something interesting about the mineral deposits. They come in clusters. So that's why you hear about mining districts. The idea is that if you find a significant deposit in a virgin territory, it is very likely that in the vicinity of this deposit, there might be others. And that's what happens with the companies. One company takes a piece of ground, finds a deposit, and then there is a rush. That's how it's called in English, a rush. Yeah. So many companies go and stake territory around the initial territory that was staked and where the deposit is. They speculate this idea. The investors know that there are good chances to find other deposits around the initial one, and they put money into these enterprises. So what happens now in mineralization is, we know there is mineralization here. So basically we might be able to extend to figure out that the mineralization goes in a certain direction based on our structural analysis and so on. So this is what it means, non-mineralization. All right, so I think that this carries the message that more and more we have to rely on these methods. Geophysics, especially because geochemistry has limitations. You'll see when we will discuss next term about these aspects. Now, these are the conclusions of what I just told you, so I'm not going to go through it. Now, let's go to the remote sensing. And of course, you are taking this course, you've seen this. Just as a very brief refresh, you see that basically from the electromagnetic spectrum, these technologies that we call remote sensing use basically this optical range interval, or segments from the optical range interval, as you can see. So the most important spectral regions are, as you can see, in the optical range. It's between 0.5 micrometers to 14. Yeah. So this basically takes us from visible into infrared and into the mid-infrared. So that's basically what most of these sensors use. Now, we also have some sensors that operate, and this already, you start the radar and all this, in the microwave range. All right, so 2 millimeters to 0.8 meters. And what is important with these technologies, they try to take advantage of the windows, of the windows. So where we can get the backscattered radiation. So as you can see, we get the backscattered radiation. We have the solar radiation, and it is backscattered from the Earth's surface. And basically, you see where it has the highest intensity in this curve in A. And then if we look in B, we can see basically the transmission of the radiation through the atmosphere. And then we can see that we have bands where we have blocked transmission. And then we have other bands where we have the transmission proceeding. Yeah, so the sensors take advantage of this. As you can see, what is interesting, before we look at the technology, we can look at nature, and we look at our eye. Yeah, and you see the human eye, yeah, which is very well geared towards this peak of the backscattered solar radiation, yeah, in the what we call visible. We call it visible because that's where we see. But the human eye, actually, it's a remote sensing sensor, which speculates exactly this. And you see the transmission is pretty good in the visible. So, of course, we extended our sensors, and then we did it with photography, and then with better and better sensors. And that's what we do. All right. So this is just a refresh of something that for sure you've seen before. Now, in mineral exploration, this is this is a fundamental principle in remote sensing methods, yeah, because we take advantage of the fact that different materials will reflect differently. Yeah, the intensity of radiation that comes from different materials is different. So basically, this depends, in its turn, it depends on the actual physical attributes of the material. So we take advantage of this, and in mineral exploration, as you can see here on the right, for instance, we have the reflectance spectra of carbonates, and you see, for instance, if we are trying to find something and we know that a certain type of carbonate is associated, let's say, or part of alteration, we might be interested in mapping the distribution, the distribution of this mineral. So we can take advantage of the absorption bands, for instance, where we get less reflected radiation if the material contains a lot of this mineral. So that's the idea that is used in mineral exploration. We try to map the distribution of different minerals, basically. And these minerals, we can link them to something associated with certain mineral deposits. All right. So in terms of what is available and what people use, as you can see, we have these panchromatic images that we can get. Yeah, so the sensors have, like the satellites have a sensor which is a panchromatic. So basically it has a wide range, so we don't get spectral information. We don't focus on certain bands. But this is good at least to have a base map, to have a base map. And then we have the multi-spectral, and the Landsat satellites are very good on this. And with the multi-spectral, we can focus on, for instance, iron oxides and especially clay alteration. And alunite is a mineral which is associated with the alteration of certain important deposits, such as the epithermal gold deposits, for instance. So people use these multispectral sensors to actually get maps of the distribution of clay alteration, especially clay alteration, or different types of alteration. And again, the Aster Satellite is very good, again, for alteration groups, specific minerals. And nowadays we have also hyperspectral scanners. And again, they are getting more and more in use for mineral exploration purposes. So that's basically the idea. Now here, this is a table which is a bit dated because it, as you can see, it's already old. To me, the year 2000 seems as if, oh, we are in the new era. So, but now I realize that there have been more than 20 years since the year 2000. So now I realize that 2004 is already old. But anyway, it carries, like, these satellites still exist, and it carries the idea. And what I want you to see here is the different ranges in the spectrum of the sensors. And you can see, for instance, they are equipped with a panchromatic one, and many of them, and then they have bands. You see, well, you see one band, like for instance here, you have between 445 and 9. So this is on a panchromatic, and then between 4.5 and 9, you get 4, separate bands. So you get sensors for that. That's multispectral. So this happens for all of these. But what I want you to see here is not this. And of course, we don't care about the numbers here. Also the resolution, the pixels, you can see them here. But I want you to look at the cost. Because the cost is always, when you will be managers in companies doing mineral exploration, the cost is always the primary thing. It's at the forefront of your mind. So the idea is how to optimize, how to spend the money in the best way possible. And as you can see, quite a large difference between the costs, So this is like the hyperspectral, of course, is expensive, as you can see. Good. So let's let's now talk on the things that I came here for today. And this is actually the use of remote sensing for mineral exploration. And here there are two main applications. One is to look at what I was telling you, the alteration patterns. And these alteration patterns are associated with certain mineral deposits. So this is one approach. People use the multi-spectral satellites to basically try to find the distribution of different alteration zones. And I'll show you what this means. Now, the other approach is to look at the structural aspect, especially. You can use, also you can use remote sensing to do geological mapping, but also what is very important here is the structural aspect. And the structural aspect is very important because most of the mineral deposits are associated with structures. That means they have structural control. And the good structural geologists make a living, actually, by doing the following thing as consultants. What they do, let's say if a deposit is found, they go and look very carefully based on the data that is available, and try to find the actual structures. That means there might be a system of faults that controls the distribution of mineralization, so that they can predict where the deposit is going and where to go and explore for more mineralization. So that is the idea. So remote sensing is very good as an initial tool for this at all scales. So let's go into, first we'll look at the hydrothermal aspect. So here is a bit of text. So what we do, we try to find what's called hydrothermal alteration. Now, I'm fully aware that you haven't taken an economic geology course, so I'm using here some words and I want to explain them. We have different, there are many types of mineral deposits. And if you start reading an economic geology book, you might get frustrated or bored very quickly because it seems that you would never understand what they talk about, especially if you look at the table of contents, because you'll see many, many things. But most of the deposits, not all, go into a very big class, and this is called hydrothermal. What this means, it means that the deposits were formed by fluids that brought elements, in our case metals, to a certain place. The place is where the deposit is. And because of a change in the ambiental conditions, that means the pH, yeah, the chemistry environment, because of the change, the metals no longer stay dissolved in the fluids and they precipitate. So that means hydrothermal means that we have an initial package of rocks, doesn't matter what the rocks are, and we have fluids penetrating these rocks, and they basically precipitate the minerals that carry the metals. Now, how do these fluids come? They come along structures. They come along faults and fractures. So here you can see why the structural control is very important. So this is a really big class. And what happens, you have to imagine people are interested because this is what provides the money, what makes a profit. We are interested as a society in getting that volume of rock that carries the metals in such a concentration that it is profitable for us to extract it. However, nature doesn't think like this. Nature doesn't think, well, we have to, this is a deposit. Nature basically has these fluids. They penetrate a host rock, and In the same way a magma evolves, if you learned in the petrology course, in the same way these fluids evolve. So let's say if they here precipitate some metals, they continue flowing, and even if they don't carry here the gold, they carry other things still dissolved there. They will interact with the host rocks and will modify them. Yeah. So this modification of the initial rocks is called alteration. So a deposit, what we call a deposit, we think only about the volume of rocks that carries the metals that interest us. But geologically speaking, we have to think of a deposit as a much more complex thing. Is that volume of rocks that was altered, that was transformed chemically and mineralogically by the percolation of these fluids. So you can imagine that now we have some deposits. The deposit is there in the center, and the fluids continue their way and modify the rocks, so modify the mineralogy of the initial rocks. And if we can find the external envelopes, let's say, of these modifications, we can vector in and try to get to the center of this volume that was altered and find where the actual concentration of metals that are of interest exists. Okay, so this is very typical for what it's called porphyry deposits. Porphyry deposits have very large alteration envelopes. So people use remote sensing. They are also large volumes. So people use remote sensing to narrow down to the volume that was altered so that then they can focus on that. All right. What they do with the remote sensing, as you can see, different processing techniques like band rationing is or band combination. This is very much used. Principal component analysis, spectral classifications, things like this. And now I'm going to show you. So this is a bit of what you'll see in the other course. I'm going to show you what a theoretical porphyry deposit looks like. So the idea is that porphyry deposits are especially of interest to us here in Latin America, because Latin America is very famous for them. Chile, yeah, Chile is a big mining country, and because of its political stability and things like this, they have developed all this mining industry. But the potential is here as well. I mean, in all the Andes and Central America as well, and in the North American Cordillera we find them. And associated, we have actually the porphyry deposits form at a certain depth in these volcanic systems. At shallower depths above the porphyry deposits, we get the epithermal deposits, very rich in gold, for instance. So it is a system, actually, that reflects the evolution of the fluids, yeah, associated with volcanic activity of the fluids. And we have two sources of fluids. One comes from the magma, and the other one is the meteoric waters that get heated and that get mixed with the volcanic fluids, and a lot of chemical processes happen. But if we were to focus on the hydrothermal deposit in general, as you can see, these are what we call the hydrothermal alteration zones. So we have different zones, and here is the mineralogy. For instance, there is a zone which is called the potassic zone. Now, the potassic zones means potassic alteration. So a lot of potassium feldspar is formed here, mineralogically speaking. You see K feldspar here. The potassic zone is very important because the higher grade ore, so the ore, basically what the higher concentration of metals, and these metals can be gold, can be copper, can be molybdenum, they are associated with this potassic zone. So you see here to the right, this is the ore shell. So if you have this potassic zone, imagine it as a cylinder, and kind of surrounding it, or kind of at the margins of it, theoretically you get the concentration of metals. And this this ore envelope is at the boundary with another alteration zone, which is called sericitic. Now, sericitic because here you have dominantly you have a mineral called sericite, and sericite is a fine-grained mica. And then outside of this sericitic zone, you have something called the argillic, argillic alteration. And here you have clay minerals like kaolinite, and you have a mineral called alunite. And outside this envelope of argillic alteration, you have a big envelope which is called propylitic. And here you get chloride epidote, so the rocks are kind of greenish. So in theory, this is the theoretical structure of a porphyry system. So imagine what happens. Geologically speaking, you might look at a system that is exposed and that suffered erosion. So today, if we are lucky and if it's not buried, some of these zones will be exposed due to erosion. Yeah, so you see, this is the present ground surface. So imagine if we were to use a sensor, we should be able to see the distribution of these zones because they have different minerals, and then we can use a reflectance spectra, yeah, to actually illustrate the distribution of some of these minerals. So this is a theory behind what people do. Now let's look at some, let's see how we are on time. 9:30, okay. Okay, we still have some time. So here is an example. Some examples, for instance, a zone in Iran. And you can see band rationing, yeah, band rationing of thematic mapper data. And you can see if we look at the reflectance of the unaltered rocks and altered rocks in band 5 and band 7, and if we do the ratio of these two bands, we can see the difference. So basically, the imaging here would show us a zone where we have altered rocks. So let's say if you start with this area, at least you'd know where to go. Yes, so that's what it helps us with. Here is again from the same area in Iran, but a different sensor. This is a Aster Satellite, and here we have basically a false color composite image. So a combination of these two bands, as you can see, 4, 6, and 8. And what we see here, and this is very nice, you see in green what is called the propylitic alteration. So you remember I was showing you that the propylitic is the outside envelope of a system, and it actually extends for large distances. So basically here it seems that you are more or less outside at the outside margins of this big system. And in yellow, you can see the sericitic alteration. So basically, sericitic means, okay, we are interested in getting to the potassic alteration zone. Where that is, we don't know exactly. But obviously, if I were to ask you, okay, you are the chief geologist, and basically your staff shows you this image, and you have to make the decision where they should go. Obviously, you should go in this area where you see red and yellow and start focusing on this area so that you can try to narrow down where the mineralization might be. You will not go here where you have a lot of green, for instance. Okay, so you can see now the use of this technology in this case. Here is another example, very nice. This comes from Chile. And as you can see, these combinations, the Aster Satellite, the bands, you can see how they are shown and what they represent. Different types of minerals. So basically, the different colors, as I put them here in the legend, reflect the phyllic alteration is a sericitic alteration, phyllic alteration. Yeah. So you see basically the different types of minerals in this triangle, in this diagram, and the colors, how they associate with these different types of minerals, and they reflect a certain type of alteration. So obviously, you see the blue, purple, and the shades of red might be of interest, not the ones of green and yellow. So the green and yellow, as you can see, is more or less here outside, and the mine is here on the inner part, in the inner part, yeah, of the system. So that's basically what this reflects. But when we discuss in class, you know, I'm showing you these nice diagrams of the systems and so on. These are models. So keep in mind that these are models that help our understanding. You know that nature is much more complex. So typically we will not have the very nice geometric forms that we show in class, yeah, of these envelopes. You can imagine that we are talking about fractures that have to allow the penetration of fluids. So obviously, the distribution of these fractures will control, in the end, the pattern of alteration. You know, at the first pass, we do have these envelopes, but they will not be perfect ellipsoids as shown in the courses. This is just for us to remember their order. Okay, now here is an example, also of band rationing, the same bands, but this is a bit of a different system in the sense that this is not a porphyry deposit. It is similar. It comes from the same type of fluids in the sense that this is an epithermal deposit. So we have a genetic link. The porphyry deposits are formed at depth, let's say 10 kilometers, and these are shallow, could be 1 to 2 kilometers. And the idea is that the evolution of the same fluids would lead to the formation of these two systems, one above the other. Now, the erosional level today in Nevada here allows, yeah, the fact that we see this epithermal gold deposit. If we were to think, there might be a porphyry one below it, but in general, porphyry deposits in absolute terms have low concentration of copper, for instance. We talk about concentrations of 0.4%. So it is not economic to go 7 kilometers. I mean, we cannot go 7 kilometers. I mean, the deepest mines in the world are 3 kilometers, maybe a bit more, 3 to 4. And those are gold mines and exploit a different type of deposits called gold orogenic gold deposits. But the idea is, even if it were a buried porphyry deposit, these are volume deposits. They are exploited in open pits at the surface. So if the erosion level is not showing us a porphyry deposit, it might be there, it doesn't help us. Okay, so in this case, these are typical gold deposits, and they have basically what we call argillic alteration. That means clay minerals. And you see basically from the geological map, this is to illustrate how we can use these technologies. So the distribution of the alteration, so these are the rocks that suffered this alteration. And look at the imagery, yeah, processed, how nicely it fits with the geological map. So obviously, now we know the geology of the area because this is a known deposit and we can do these tests. But if we didn't know, you can see that it does vector, yeah, in, so it does narrow down the search space. Yeah, so this is what is interesting. So if any of you is, let's say, less inclined to work in the field and to work next to drilling machines, you know, in this kind of environment, go into the field and in the mud and in uncomfortable conditions, you might focus on, you know, becoming a specialist in processing of remote sensing data and helping companies to initially focus on a certain area. All right. So this was, now you saw the use of the technology for finding and mapping alteration. Now, the other approach is structural mapping, yeah? What we call geological and structural. So we need, in any area where we go and explore, we need a good understanding of the geology. So this is going to help us, okay? So obviously you can see here the imagery here shows, folds. This comes from Iran, and I'll show you more from Iran. So now these are folds, yeah? You can see this is an area in Iran which is called the Zagros Fold and Thrust Belt, very famous worldwide. These are, you see from India, so you can see very nicely these folds that show offset. So obviously we can use this technology to do structural mapping. Here is another example with the interpretation of the structural interpretation based on the image that you see on the left, for instance. Now here we have, as you can see, we have a little legend, and the legend says base metal deposits. And it shows, as you can see, this comes from India, so it shows different deposits, if we can see if they are squares. So the conclusion is that, as you can see, these deposits have a structural control, obviously. So they are associated with faults, or at least fractures, that allowed the penetration of fluids and the fluids that brought the metals. Now, base metal deposits are deposits of copper, zinc, and lead, and tin. Yeah, so these are base metal deposits. Here are other examples, like you can use the satellite imagery to do geological mapping. Of course, what people do, they do an initial interpretation, but then they go in the field, because even if you can separate different domains based on the imagery, you have to go in the field to see what exactly those rocks are, yeah, so that you can basically convert your interpretation based on the morphologies that you see and different reflectivities, convert it into a geological map. And here are other examples from Iran. I'm giving you these examples because, in my opinion, they are quite spectacular, being the bedrock being so nicely exposed. So, great structural mapping. Okay, so here is an example of what's called the Great Dyke in Zimbabwe. So this is very famous. Imagine you have a dike. So the dike, it's a tabular body that was filled by magma. And what's interesting about the Great Dyke in Zimbabwe is that it extends for more than 500 kilometers. And you see it has a width of 3 to 12. So it's really great, a Great Dyke. And there are various deposits associated with this dike. Now, these deposits are not hydrothermal. These deposits, you see here the text, the PG means platinum group element. So platinum group elements are like platinum, yeah, and osmium and rhodium, things like this. And the idea is that chromite deposits and platinum group element deposits are what they are called magmatic deposits. So basically, they form directly from magma. Now, we have to have a certain type of magma, mafic, ultramafic, to have these deposits. So they are associated with these intrusions, and especially the layered intrusions, mafic, ultramafic intrusions. There are two very famous in the world. One is in South Africa called the Bushveld intrusion, and the other one is in Montana in the United States called the Stillwater. So these have been studied a lot, and of course there are many other localities with these deposits, but these are famous geologically speaking. So the Great Dyke in Zimbabwe has such deposits associated with it. And if you were to look with the satellite imagery at it, you see it very nicely going from north to south. And what you see also very interesting here, you see some faults. So there is a very important, very significant fault that you can see how it folds this segment from this segment here. And also you see a river going through this. Now, rivers and these streams, they would often speculate zones of structural weakness. So in many cases, the river channels are associated with fracture zones or fault zones and things like this. There is another one, as you can see, another displacement here in the Great Dyke. So these are the type of things that people can do. Now let's look at something very special. I want to tell you before we go into this that if you can, come next Monday to the seminar, because I will host my friend Vadim Galkin and my mentor. He gave this talk last time in the seminar course, and JB was running the seminar. But I asked him to come and give it one more time, so people who are in this term registered in the seminar course, they can see it. The reason being that he does something that is, in my opinion, very important. It is linked to mineral exploration, and it is used only by very few people. So, and he's a specialist in this. So the idea is I invited him to give this talk, and he will give a talk on linament analysis. So what happens? Linament analysis is part of this structural interpretation using remote sensing data. But the idea is that someone should look for linear structures. So linear structures can be not only faults and fractures, can be geological contacts, can be features. If we look at the vegetation, let's say, and the vegetation has, we can see two domains with two slightly different colors, and then we can see that the contact between the two domains in the color of the vegetation is like linear. What this would show us is that we have a domain where the plants get some elements from the ground, and we have a domain where the plants get something more or less in as nutrients, and that generates a difference in the color image. And that shows us geochemically a difference. So it could be a geochemical contact, yeah, for instance. So any linear features that we can find in different types of imagery, and this means not only images from the satellites, but also geological maps, geophysical data, things like this. All right, so you see the list of data sets that can be used for linament analysis. Now, what happens? Someone has to map all these lineaments, classify them. Some are more important, like major faults, for instance, or contacts. Some are very small. So a classification is made. You can do it manually, and of course it's tedious, it takes time, or you can have software to do it. Now, the problem with the software is that it's not always successful. We like, nowadays everyone talks about artificial intelligence and machine learning and so on. Personally, I think that our capacity of discrimination, especially when we come to things like nature, where we have variance, is better than the capacity of machines. The machines can repeat things, yeah, can make our tedious tasks better, but we are actually better judges in many instances. So what happens is we map these lineaments, and then we use a certain way of calculating the density of lineaments in a certain unit area. So we get a map of the density of these lineaments. Now, if you have a higher density, you have more intersection between lineaments. So you have a larger probability that fluids that came along one of these lineaments at the intersection with another fracture, for instance, there was a change in the chemical conditions, yeah, a change in the pH, for instance, and that would lead to the precipitation of metals. So the idea is people have seen that in many instances, the deposits are at locations where you have more lineaments coming together. But again, this being nature is not like in engineering. Sometimes it's correct, some other times they are associated, but not necessarily where you have the highest density, you have high density. So I'll show you some maps. So that's why it's a very difficult science in a sense and not well understood. And it's at the frontier of research for courageous people who try to embark into this. So let's see what I'm saying here. I'm telling you that many ore deposits are structurally controlled. And when I say epigenetic mineralization styles, I'm teaching you a new word, which is epigenetic. And epigenetic is the opposite of syngenetic. So, for instance, syngenetic means something formed at the same time with the host rocks. So, for instance, a magmatic deposit is formed at the same time with the host rocks, with the magmatic intrusion. But the hydrothermal deposits are epigenetic. You must have initially a package of rocks, and then you have later fluids coming into them and precipitating the metals. So epigenetic mineralization styles, they are structurally controlled because the fluids must use some conduits. Yeah, so that's the idea. So here are some examples. You can look at the geological map. Look at this map, for instance. This is from a fold and thrust belt from a Proterozoic orogen in northern Canada, for instance. You can see many structural features here, many faults. So the geological map already shows you many lineaments. You can pair the same area with a magnetic map. What you see here on the magnetic map and you don't see on the geologic map, you see many linear features trending here from the northwest to the southeast. What they are dikes. No, they are not as big as the Great Dyke in Zimbabwe. They are much narrower, but there are many. This is a swarm of dikes. The dikes have formed along fractures. Yeah. So basically, you can see a fracture set. Yeah, which is all oriented northwest to the southeast. Very intense. So these are already lineaments. Now look at the magnetic map. You might see that there are other dikes. For instance, there is one here, which is cross-cutting perpendicularly the initial set. There might be others. Now, there are some oblique that I can see here. Also, there are some magnetic domains. And these magnetic domains, for instance, this one might be a dike from this domain with lower magnetic intensity. Or here, this could be lineaments, like this is a lineament, for instance. So someone would map all this, and then they would do the lineament density map in the end. So these are examples. Let me show you other examples. You take the topography. Yeah, this is a topography. Again, this comes from northern Canada to give you an example. And I'm showing you different streams. So you see these little rivers. Yeah, we have here in this region a major river, which is called the Coppermine River. But people don't know about it because it is in a region which is deserted. You don't have settlements, so no one talks about the Coppermine River. But it is a big river, and what happens, you have all these streams. Now look at this stream, like look at this. This is a lineament, and here on the other side there is another lineament. So obviously there is a lineament here. The river is speculating something in basically in the ground. And other like little lakes, and you see the shore of the lake, you see it here, or here the river, and so on. Now you can take an aero photograph. Yeah, you can take an aero photograph. Again, you look at the lakes, you see this would be a lineament, a small one. This would be another small lineament, and so on. So people who do this must have a lot of patience, but it is very interesting, actually. So in the end, what people do, they map lineaments. So this is a simple example. This, as you can see, it is from a region in the Philippines. And someone mapped the lineaments. Of course, they show us the principal ones. Probably they had a lot more, but they are not shown at this scale. And then you see all these polygons, which basically are polygons, each of them having a certain fracture or lineament density. Yeah, so you see the polygons that have the highest density are the black ones. Yeah, and here what is shown with these triangles. Yeah, what is shown with the triangles, these are epithermal gold occurrences or deposits. So if you look at this, as I was telling you, they tend to be in the areas with a higher density of faults or fractures. But it's not an exact science. You see, it's not, you might expect them to be only in the black polygons, but as you can see, they are not only in the darkest polygons. Actually, I don't see, like the really darkest ones don't even have one, but they are somehow nearby. So this being more or less statistical, obviously there is a discrimination here. The fluids came along a certain fault or a certain fracture system, and then maybe at certain intersections they were deposited. So as you can see, they tend to line up here. Yeah, so they tend to line up. So obviously this fracture system or fault system, which is northwest to the southeast, well, northwest to the southeast, basically tends to be the controlling one. But now, are they deposited the intersection with the oblique cross-cutting ones? I don't know. At this scale, I don't know. But as you can see, there is a correlation, okay? But we always have to take into account the statistical aspect. You are not going to see the deposits in the areas with very few lineaments, yeah? You are not seeing them here, obviously. All right, so this is an example. Now, this is another example where I'm showing you what I was telling you here. Here, we do have some yellow circles. You see the yellow circles represent gold occurrences. So we see the yellow circles. Now, these examples come from Egypt, from the desert in Egypt, close to the Red Sea. And what I want you to see here is the difference between a line density map obtained by manually mapping the lineament. So someone looked at the data they used to map the lineaments and then to do the density map. And then we can compare it with basically the line density map of lineaments that were extracted using an automatic method, so using a software. And the conclusion, actually, if you look at the conclusion, it says, very interestingly, it says, the automated extraction technique produces short, dense lineaments that are difficult to relate to tectonically significant structures. These results are not necessarily accurate. So I wanted to give you this example to see that it's not always that the computer will understand the geology in the same way we do it, because we spend so much time trying to understand and integrate different things in our minds. So as you can see, you have higher densities. Now where you see these yellow circles, you do see kind of higher densities, yeah, in these areas. Anyway, which is a purple. No, sorry, which is a blue, the blue. It's higher. Whereas here it shows kind of only low densities. Anyway, complicated science. I will finish today with an example that comes from Portugal. This is a complex study, but just to show you how they used different data sources. So they used Landsat, and you see different band combinations. You see them 1, 2, 3, 4 different band combinations. And also they used shaded relief maps, okay? And they basically took the time to map the lineaments. And you see the regional lineaments, the local lineaments, then they combine them. I'm pretty sure that if we want to get sophisticated, we will have to put weights to the lineaments. Probably a larger lineament is more important, so we might have to put a weight. And this, in my mind, this is an area of research. Yeah, this is an area of research. We should put weights to the bigger lineaments, which seem kind of more important, because probably they are responsible for bringing the fluids. So the final conclusion of this study, after they combined all the elements, they did a lineament density map, and the map is this one with these shades of blue. And as you can see, higher density is a darker shade of blue. And on this map, they plotted the mineral occurrences or deposits from the area. You see them in red and yellow, depending on the dominant metal. It can be gold, or it can be, as you can see, tin, or tungsten and tin. Now, what is interesting, you'll see that they do get associated with the areas of higher density. Especially, it's very interesting that the tungsten and tin ones here, where you have the highest density, we see them here. But in general, as you can see, they do reflect a certain structural pattern. So, in a sense, it is a frustrating science. In a different sense, is a very interesting at the leading edge science, because always the question in mineral exploration is how to predict, how to narrow down the range of possibilities so that we can spend the money in such a way that we can be more successful in finding the mineral deposits. So this being said, this is it for today. I hope you liked it. And if you have questions, please let me know. If not, I wish you a great day and a great weekend. And hope to see some of you on Monday at the seminar. All right, so thank you very much. See you. Welcome. See you, Sergio. Welcome, Isabella. Thank you. You're welcome. Welcome, Sarah, Juan Pablo.